Sure. So, thanks for coming, and after enjoying some reggae music, we can finally start talking about Project Reactor. So, a few words about me. I'm Sergei Egorov, live in Berlin, and I work for Pivotal in Project Reactor team. So, what I'll be talking about today is like the direct result of what we've been working on. I'm also organizing Spring User Group in Berlin. So, if you are in Berlin, just come and say hi. I'm also test continuous co-maintainer, which is kind of orthogonal to what I'm doing daily, but it's still a great project, and I'm happy to participate in the project. And I'm into development tooling and stuff like this, as you can see, basically. Also been doing microservices and other stuff. Before we start, I would like to ask you, on this slide, these talks, what do they all have in common? So, what's the most common thing about these talks? Non-blocking, maybe. Out of the talks, I'm not sure, maybe the talks were non-blocking, but I'm not sure. Well, the most common thing about them are great speakers. Seriously, these are really smart people, and they know what they're talking about. But another thing is reactive programming. And these are talks from Vox Days, Minsk, where we all are. But what I want to say is what they were talking about was how great reactive programming is, and it is great, and how performant it is, and what can you do when you need to, create a high-performance server, or how you can benefit from reactive programming. But instead, would like to focus on the development experience, because after watching the talks, you may have a feeling that, okay, reactive is great, but it's a bit hard to, start with sometimes. And I don't know about your experience, your very first reactive programming experience, but mine was something like this, or in my case, like this. So I had no idea what I'm doing. I just started, and I thought it would be easy because everyone is talking about it, but apparently it's not that easy. And my first attempt was, okay, I know runnables, because everyone knows runnable. Runnable interface is a super popular interface in Java. Everything starts from runnable. Thread starts from runnable, and so on and so forth. So we know runnable, right? And I discovered that there is mono from runnable method. Okay, let's try to use mono from runnable. Yeah, okay. Why didn't you work? What happens? So I was really surprised because nothing happened, literally. I tried mono from runnable, I passed my runnable to mono from runnable, and I expected my system out println to print something, because the best way to debug something is to print something, right? PHP style. This is how I learned that apparently in reactive programming, everything is lazy. And I really like it because I'm lazy too. So it's very close to the way I think, but also I had to learn that we must subscribe, otherwise nothing will happen. Literally nothing will happen. If something happens before we subscribe, then we break the specification. So I learned this thing and a few others, and 1 week later, I was feeling like reactive seer. So I was talking about reactive programming all the time. I was quoting popular reactive folks. I was going to lunch with my friends from a company and telling them how reactive programming is great. This is how I lost most of my friends and started going to lunches alone. But anyways, another week, one more week of production experience. The picture of me was a bit different. Yeah, this is how I learned it the hard way. And apparently, there are many things that may go wrong. And what could go wrong with reactive programming? Well, if you attend the talk, and the talk says something like the good and bad and ugly parts of reactive programming, most probably the ugly part will be talking about exceptions. And it's indeed a bit ugly. And to demonstrate the problem, I would like to use this very simple code. It does nothing than just iterating over a set of integers, or generating a set of integers, and expecting a single integer, subscribing on parallel subscriber, and doing the subscription. Because as I said, everything is lazy. We must subscribe to make it start. So that's my code. The code is located in com.example demo example class. And if I run this code, I will get this message. Okay, let me focus on the most important part, the package. Because when we see an exception, we start going one by one until we find our package, the package we know, package from our company. And as you can see, my file is located in com.example demo package, but com.example demo is not represented in this tag trace. And the message is a bit weird, like which source? So, okay, source emitted more than one item, but which source? I don't know, do you? Okay, if you have one .single operator in your application, and this application is some really small microservice, but in this case it's rather a nanoservice or a picoservice, whatever, then you may know that, okay, that .single operator I was using after reading the documentation, but most probably you don't. And of course, where is my package? Seriously. We are in Java. We are obsessed with exceptions. It's okay to see a lot of unnecessary things in the exception, but where is my package? I can see it. And many other questions we can observe in this picture without any answers. Before we go into more detailed explanation, I would like to talk a little bit about assembly and subscription difference, because if we are lazy, then we first need to assemble something lazy, and then make it work, like make it start. So, assembly phase is the very first phase of any reactive code. This is how we build our pipeline, and reactive code is essentially a pipeline. We describe how signals should flow through our application, right? So, okay, I call this method, some other method, and some other method. These are normal method calls. We call them as any other Java code, and we go one by one. So there's no special exceptional case in JVM for reactive programming. No, we simply call methods. We build our pipeline. We build it, we see subscribe on here. It contains subscribe word, but it doesn't mean that it will subscribe, by the way. It just happened to contain subscribe word. But what it does, it says that, okay, when we subscribe, it should start on a separate thread pool, which is our shared parallel thread pool. And boom, we subscribe. Now we trigger the subscription phase. The subscription phase is the other way around, like we go from bottom to up, right? Because now we call .subscribe on the very last element in the chain. And, well, I tried hard, but I failed finding a good emoji for subscription or anything else from Reactive specification. So this kitty, little kitty, will be our subscription, okay? So you see kitty, you think of subscription. So kitty goes to mono-subscribe on. Then it jumps to onto the parallel thread, because we say subscribe on parallel pool, and parallel pool will contain a thread. In this case, it will be parallel 1. And then we go back and back and back in the chain until we reach our producer, our source of elements in this chain. Same issue, the emojis, this fish will be our subscription, okay? So, our producer says, hey, if you want to receive something, here is subscription you can use to receive stuff. So subscription goes back till we reach the point where we subscribed, and our subscriber will be requesting something. If you attended yesterday's talk about RSocket, then most probably you have seen a really nice demo of back pressure. And this request is actually what makes back pressure work. Basically, when you request something, you're telling the producer how many items you're ready to consume. And in this case, I'm requesting as many items as you have, because I'm just using .subscribe from my framework, and my .subscribe by default will request the maximum amount. So the request goes back in the chain, and it's important to remember that every signal in reactive streams goes through different decorators of the original publisher, and it's not like we request directly from Flux range. We actually request from subscribe on, and subscribe on will request from single, and so on and so forth. When Flux range receives a request, let's say give me 5 or give me long max value or whatever, it will start emitting items. And the first item will be just 0 integer, because, well, that's how our range is defined. So 0 goes back, it reaches the subscriber, and now Flux range will emit a second one. No error will happen yet. It will go to Flux filter. Okay, Flux filter does not define any restrictions to the items. Just give me as many as you can, and I'll filter them, and I'll pass them down. But when we attempt to, Flux map, but when we attempt to emit from Flux map to monosingle, so we say, hey, monosingle, here is your integer, and monosingle will be like, whoa, 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 wait, my user has said that I should not receive more than one item. This is how .single operator works. And it throws an exception, because that's an exceptional case. But as you can see, the exception is being thrown on a separate thread. It's not the same thread as the main one, as the current thread where we triggered the subscription. So we completely lost the information where the subscription has happened. And that's a problem, I would say, because now we cannot connect two dots. Our assembly and our subscription, our runtime phases. And to demonstrate it in code, I would like to do a short demo. I have a very simple Spring Boot application here. It's super simple one. People at the back, if you don't see the font or anything, just tell me, I'll make it bigger, but I think it should be fine. So we have an application, and we have a controller. And this controller defines a response as Flux just hello world, basically two signals, two strings. We say single, because we thought that single will give us one item, so something like first item. But apparently it gives an error, so we misused an operator. Maybe we wanted to use .last or something. And we subscribe on parallel scheduler just for the sake of this demo. If I run the application started, and now if I make a request, oh, not this one, but this one, so I'm just triggering get request to /hello, then we get this not that beautiful exception in the log. And as you can see, so IntelliJ would highlight my own classes if there are any in the stack trace, but there are no such. Like, okay, Reactor core internals, then Java util concurrent, thread run, but I cannot find my package here. So the same issue demonstrated. And what I can do, I can use one of Project Reactor's features, and this feature is checkpoint. So let's say I put a checkpoint after single, and if I restart the application, then we see that this error has been observed at the following call sites. And in this case, we only have after single checkpoint. That's already something. That's something we can even push to production, and it's going to work. But it's a bit insane, to be honest, to put these checkpoints everywhere. Like, imagine your code if every operator would have the checkpoint, my producer, and you have to think like what to put here, right? Like, if it will be always, if it always be like I don't know, foo bar, hey, please buy me a beer. So these checkpoints are not really helpful, right? And they create a lot of noise in your code. It's okay if you need to checkpoint with your user ID, it's really helpful, but for the sake of debugging, it's not really helpful. So what else can we do? We can, of course, use Hooks.onEach Operator debug. That's a built-in functionality from Project Reactor. It's super helpful, but it's not designed for production. Please do not use on-operator debug in production. But in testing, it's fine. So if I want to test my application and say I receive a report that this query fails, so I start my application locally, I run the same query, and I get the information I expect. As you can see, now we have many more details here. So first of all, we have a reference to our application automatically. So we don't have to put this checkpoint anywhere, and we can click, and boom, I go to single, then I go to subscribe on. Very convenient, right? It's already something, because now if some exception happens, we can at least backtrace it to the original assembly phase, and we can say that, okay, if this exception happens here, then I can put more breakpoints or something, or add maybe logging to check some race conditions or whatever, whatever works for you. So the issue is solved for debugging or for testing, but what about production? And for a really long time, this issue was, or this limitation was, like we had to accept this limitation. Like, yes, you can use it in development or testing, but you cannot use it in production. And if you are in production, the best you get is checkpointing. We started thinking, what can we do? So obviously, we cannot leave it like this, because it's such development experience when you only see this actually sucks, I would say. I mean, it doesn't help. We could, of course, we can as well drop this exception altogether. Like, it doesn't provide any value. And you start thinking, how other systems solve this problem? And a very similar approach is automatic instrumentation in the APMs, application performance monitoring systems. And if you're using Dynatrace, New Relic, Instana, or any other instrumentation agent, then most probably you're already doing bytecode transformations. It's fine. The way Java works, it allows us to do the bytecode transformations. So why can't we apply the same knowledge about the bytecode transformation to the debugging experience? Why not, after all? And that's what we did. So if you add a dependency, and this dependency is this one, it's called Reactor Tools, and part of Reactor Tools is a debug agent that will automatically instrument your code. If we do it like this, just by changing this line from Hooks.onEach debug to Reactor debug agent init, we'll get the same result and even more, but I will talk about more a bit later, with a very low overhead. This overhead is so low that you can use it in production easily, because now, instead of oh, and I haven't explained why on-operator debug is slow, actually. And to explain it, I will tell you one thing. Every time you call something like .single, .map, .subscribe on, or any other operator, we take the current stack trace. So new exception gets stack trace, or stack walker, walk stack, but it's extremely expensive in JVM to capture the current stack trace. It has a lot of native calls, and it adds a significant latency. It actually will add around 50% of latency to your application, just because we cannot do it when the exception is thrown. We must do it at the assembly phase, and it means that even if your application is like super great application that never throws any exception, then we'll still be doing this stack trace captures, and it's expensive. But here, instead of doing the stack traces, we instrument the code and we add special markers, and I have slides about it. As you can see, we can also capture some automatic checkpoints. Sorry. So if I make it bigger, we capture some automatic checkpoints when you just return reactive type from some method, let's say return flux or mono, and it's really helpful when you have web client, for instance, and you have body to flux, and you want to know where this body to flux was triggered, was executed. How it works. So, for our previous example, we instrument the code with Java instrumentation at the bytecode level, and then for every operator call, we add, with a bit of magic, a special automatic .checkpoint like method call. And now, when you build your pipeline, every operator will receive call site information where it happened. So in this example, flux range will be marked as example.java line 16, single line 17, and subscribe on line 18. Now, when exception happens, we have this information as static string, so very low overhead, and there is no, we don't have to operate the stack traces anymore. We know exact place where it happened. So first demo outcomes. You can use .checkpoint, and it's still useful, let's say, when you receive requests from users and you want to mark your reactive chain with user ID. So if you know the user ID from the request, you can, for instance, add a checkpoint, user ID equals this, and then if error happens, you know the exact user ID who was affected by this error. Then, read about Hooks.onEach debug. It's still helpful. You can put it in your tests or when you need to quickly debug something. But if you need if you want to improve your production experience, please use Reactor debug agent, because it's so much better, and we will release a set of benchmarks. We already did, but I'm not gonna tell you the numbers, but we did a set of benchmarks, and the overhead is really, really low. We have some companies running into production already, by the way. And if you're curious about this subscription and assembly difference, you can read Simon's post, which is a really great one, explaining a lot more than just this KT and fish stuff. Second thing, blocking calls. And I want to tell you that if you ever took a dump of your threads on your running JVM in production, and if it looked like this, with a lot of red bars, then most probably you have a serious problem, no matter what kind of application you are running, asynchronous reactive or just classic blocking one. Because as you can see, most of the threads are spending time just waiting for something. But if for a classical blocking application it's not a big issue, for reactive programming it is, and I would like to explain why. How Reactor schedules the tasks. First of all, we have 3 default thread pools. Parallel pool for running tasks in parallel, obviously, and it consists of n threads, where n is the number of CPUs you have. Let's say you're running in the cloud, you have a very small container, you have 2 CPUs available, then we have thread pool of 2, I think. If you're running some really big machine, or please don't, but maybe some mainframe or anything, then you will have a lot of CPUs, let's say 40, and you will have 40 threads available. Then we have a single scheduler. And this single scheduler is something like a singleton scheduler. It will always have just 1 thread, not less, not more, just 1 thread. And Elastic Scheduler is a special type of schedulers that will automatically add more threads to the pool if all the threads that already allocated by the Elastic Scheduler are already working on something. I have a question for you. When you have mono delay, which scheduler is being used? Is it single? Parallel? Maybe Elastic? Because we don't know what's going to happen, right? Like, we are not in control of users' code, so we are implicitly applying scheduler here. So, raise your hand. Single? Parallel? Elastic? Parallel. So, parallel scheduler is being used because we have, by the definition of reactive programming, that everything must be non-blocking unless you explicitly specify otherwise. there is no point of using single scheduler when we have more threads available. We just run everything on parallel schedulers, and some of the parallel threads will do the job, but we don't really care which one. We are not Node.js application after all, where we run everything on a single thread. We can utilize native threads easily. So every non-instant operation will be running on the parallel thread. That's something to remember, because people sometimes think that it happens magically without involving any threading or anything. No, it's parallel scheduler. So if you have just non-blocking execution, everything is fine. So you schedule tasks, it works well. As you can see, we have some green blocks, and green block means it's good. It's non-blocking. It just consumes a bit of CPU to start some asynchronous query or just do some mapping from one type to another. So it's non-blocking, all good here. But if your execution is blocking, then for this thread pool with 4 threads, we will have it, okay, we got non-blocking task, all good. This non-blocking task said, okay, I want to schedule 2 JDBC calls, and these calls are blocking. So we will block 2 threads. Then another task comes, and it says, I also want to run some blocking calls. And this blocking call says, hey, you need one more blocking call because of n+1 issue. And here comes a third task that says, okay, now I need to run 4 queries. And there is a problem. The problem is that no more tasks will be scheduled if you already blocked all the threads you have. Let's imagine that you have a framework that accepts the request from the users on the parallel thread, and now the request comes in, but you have no threads to handle this request. Even if this request is like respond with not authorized, you will be waiting for this task to finish, and parallel 4 thread will handle the next task when it's ready. But for this duration of time, and as you can see, I'm not using the timing here. It can be 1 millisecond, it can be 1 second, it can be 60 seconds. We don't know how long we would block. But no more processing will be done if you already blocked the threads. How can we fix it? Well, obviously, you can fix it by not using the blocking APIs. But in Java reality, we cannot. There are some either legacy or just not updated APIs in Java that cannot be used in a synchronous fashion. But you can use custom thread pool. So we said that you should not block the main thread pool, the parallel one, but it doesn't mean that you cannot create another one and let the operation system manage the task switching. It's not as performant as non-blocking, but still good. So let's say we receive a task, and now we schedule everything on a separate thread pool with 2 threads, custom 1 and custom 2. Then another one comes, and as you can see, it submits some tasks, but the tasks will be executed right after the tasks from the previous one. And another, and all good here. So we're good. The only problem is that if your application, what it's doing is simply submitting blocking tasks to a custom thread pool, then you may have a problem with the memory. You may get out of memory because to submit a task to a scheduler, you need to store the task in a queue. You cannot just put it somewhere, you cannot upload it to file system, or actually you can, but that's not going to be efficient and performant. So usually put it to the queue. And this queue will eventually overflow if your tasks are blocking. But if your tasks are mostly non-blocking and some of them are blocking, then it's totally fine to move it to a separate thread pool or use the elastic thread pool, because elastic thread pool will just add more threads. Let's do another demo. I have the following code here. And what it does, it creates a range from 0 to number of processors I have. Remember this n, where n is the number of processors, so this is my n, basically. So my n is the number of processors I have. Then I subscribe on parallel scheduler to demonstrate the issue, and I'll be mapping every signal. And in this mapping, I'll be using a blocking API. In my case, I'm just using countdown latch that blocks here, as you can see. We even have to catch this interrupted exception, which is a good indicator that it blocks, actually, because someone may interrupt like the blocking procedure we are running. And to unblock the processing, I'm starting a timer with mono.delay, and once it's done, I'm just counting down the latch. Pretty easy, right? And I'm waiting till the last one. So, how do you think how long will it take to run this code? Let's say 1 second or less. Some hands. 5 seconds or less. 10 seconds or less, or around 10 seconds. It's actually funny that someone raised the hand because I never mentioned how many cores I have on this machine. So new information, I have 16 cores on this machine, and who thinks that this code will run in less than 16 seconds? Let's test. I run the code. I have a feeling that nothing happens. Let's take a look at the threads. And as we can see, every parallel thread is parked on something. So we are waiting for something, and the test is waiting for something. So apparently, this code doesn't work. Okay, I go and I change this code. -1. Now I will be running 15 tasks. We wait. Yay, succeeded. We can push to production, right? The test is green. So I can even put a constant here, like 15, so that this code is less CPU dependent, right? So we depend on CPU less, so all good here. But it runs for too long, 5 seconds. I have no time during this presentation to wait for 5 seconds, so I'll reduce it to 5. And okay, I just changed it, but okay. I'll reduce it to 5. And the 5, super fast, 1 second, a bit more than 1 second. Cool. So it runs. Yes, there are some issues with the blocking APIs, but in general it runs, right? It's all good. But now imagine we deploy the code to production where we have only, let's say, 4 CPUs or 2 CPUs because we are cloud native, we are running in containers, more containers, smaller size. So inside the container, I will have a parallel thread pool with the size of 4, let's say. And now we deploy it and we receive on-call notification because our service no longer accepts any requests. And we are panicking, what's going on, what's going on? The tests are green, everything is fine. And maybe we were running on staging, and on staging we have 8 CPUs and it's again fine. But in production, something went wrong. So, what can we do? Obviously, we cannot detect it somehow externally. We could, of course, do the code review, and every time some developer does a blocking call, we're like, please don't. This is the blocking code, do something with this blocking code, but actually that's quite expensive. Imagine every code review, you spend more time just checking for the blocking calls. And that's what I did, actually. You can also, I don't know, do something else, but in general, even the most experienced senior developer who knows reactive programming for years may actually miss some blocking call during the code review, and your production will go down. So we cannot rely on the human factor of this problem. But instead, we can use another tool we introduced, and the tool is called Blockhound. The Blockhound is a tool for exactly this problem. It detects the blocking calls, and here I'm using the JUnit platform integration. You can also just call it with blockhound.install or use some other means of applying the Blockhound, but here I'm using the JUnit platform. Now, if I run this code, my test no longer passes because now I receive an exception saying that there is a blocking call. It's not even await. It's actually unsafe.park. This is how await is implemented. It parks the thread and waits for some milliseconds, in this case infinitely. And I see the stack trace. I see the exact place where the blocking call got triggered. And I can go through the stack trace, okay, cool. So now I see that there is unsafe call. Cool. And it transforms your pull requests and your tests from don't miss a blocking call to something like make it work. Make it pass the test. As long as it passes the test, okay, there might be issues with the business logic, but at least you're not going to destroy our service. And I think that's pretty cool because I believe in automation, especially in test automation, and less things we need to do as code reviewers is always better. And I would like to explain how Blockhound works because it's a bit more advanced than just instrumentation, but it's also instrumentation. So let's say we have thread.sleep method. And thread.sleep is a really popular way of destroying your reactive application. A lot of requests, a lot of support requests come with something like, my application is slow. And then you check and you see that, I don't know, for calculate time between 2 points in time, they just, for 5 seconds, they block the thread, and then like before thread sleep and after thread sleep. Okay, cool. This is how you get 5 seconds duration, let's say. So we have thread.sleep. And as you can see, thread.sleep is a native method. We cannot even instrument it with standard tooling from Java instrumentation. But there is a trick. We can make it a private method and rename it and create a Java method, sleep. And your code will be calling thread sleep. And thread sleep will be delegating to the original native method. So now we can intercept this call with something like Blockhound runtime check blocking, and we have the information which method, which modifiers did it have, and stuff like this. So let's focus on this one, check blocking, because it's not just throw an exception. There are some cases where we don't want to throw an exception, and how blocking check works. So first of all, it's implemented as a native agent, and we check if the current thread is tagged as non-blocking or not. Because it's totally fine to call thread sleep from your test, let's say, or from the blocking part of your application. Why not? Or any other blocking method. Under the hood, the JVM uses blocking methods a lot, actually. So we cannot just avoid them. But if the current thread is non-blocking, then we walk the stack trace until we find other whitelisted or blacklisted method. Again, why? We are saying that there is a blocking call inside a non-blocking thread, just throw an exception, right? But not really. Let's say you have SLF4J and you want to log something, and to log, you're going to use a blocking method, system out println. Or this is not a blocking method, but some other one. So to write something to the console, you have to block your thread for a really small duration of time, but still you have to. You can, of course, use some reactive-friendly loggers, but that's not the case. And there are a few other examples, like you need to generate UUID, and UUID will by default block. And it will create a blocking read from security randomizer. So anyways, let's say we have unsafe park. So we iterate the stack trace, and then we see unsafe park. Okay, cool. Then more methods from JavaUtil concurrent logs package. We don't really care about them. We don't know. We cannot make any assumptions about them. Our code, nice, but again, we cannot say that our code should always be non-blocking because we also invoke other methods. Some Reactor internals, again, no control here, but when we finally reach the frame, marked as disallow blocking calls inside. And in this case, we just wrap every task submitted to Project Reactor with a wrapper, which does nothing but original runnable.run. But now we have a special marker. And now we can say, okay, the first frame known to us says that there should be no blocking calls inside me. And we got one. So we throw an exception now. By the way, have you noticed that this code looks like an integration? Otherwise, we would just use some built-in classes from Project Reactor, right? But here we are not using built-in classes, we just have our Reactor core scheduler, Reactor blockhound integration. So, it's important to remember that blockhound is not just for Reactor. We need the interoperability with other reactive frameworks. We need to integrate with Netty. And what's really cool about blockhound that this project is from Project Reactor team, but it works with RxJava. There is an ongoing conversation with Kotlin coroutines team so that if you run blocking calls from coroutine, and you shouldn't, but if you do, then it will throw an exception as well. Netty is a non-blocking processing framework, and if you block threads from Netty thread pool, then you have problems. And basically, any Java library can integrate with Blockhound. Scala folks already considering it for ZIO thing or some other project name and a few other projects from Scala. Second demo outcomes. First of all, blocking calls are bad. Remember it. Like, it's always bad. This is why we have projects like Project Loom now that works on making blocking calls super lightweight because they will be blocking not threads but fibers. And I really hope that my grandchildren will be able to use Project Loom because it's gonna take a lot of time to rewrite half of JVM internally to make it non-blocking, to make it fiber-friendly. So, blocking calls may sneak into your production system. So, the test is passing because you had more resources in your machine than your production, but your production may go down. And you can use Blockhound to detect such calls. It's a very simple one. It does not add a lot of overhead to your tests or even your environment. So what I demonstrated is just 2 additional method calls, one Java call, which is being inlined by GIT, and another one is a native call. But keep in mind that thread.currentThread is a native call. So don't be afraid of native calls. And every logger users use thread.currentThread when they log because they see the thread in the log line. So don't be afraid of native calls. And if you have to run some blocking calls for some reason, just use a separate thread pool for them if you must. Just offload them and refactor later. Use projects like R2DBC and others. There are a lot of activities in this space to make it non-blocking everywhere and reactive friendly. Some of you may say right now, like, nah, I don't care. I use asynchronous APIs everywhere. My application is great because every method I code in a synchronous way and I know what I'm doing. Yeah, that's a good statement. That's how it should be. But are you really sure it is so? Have you ever checked? And any Kafka users here? Okay, some. It's getting popular. It's been popular and gets more popular. So in Kafka Producer, we have Kafka Send. And as you can see, there is callback. So callback sounds like Node.js, right? We have callback means that we run something and then we receive notification in the future. And it's indeed a synchronous way of sending messages in Kafka. So if you read the Java doc, it says asynchronously send a record to a topic. So yeah, okay, I use a synchronous API here. No, you don't. No, you don't. And okay, I see some eyes saying to me something like, nah, it's some small synchronization, some, I don't know, concurrent hash map maybe or something, so it's not a big deal. And this is a known issue, by the way. It's not just something I came across. It's a known issue for more than 3 years. So I went to the implementation, I checked the implementation, and the implementation says wait on metadata, and it passes max block time milliseconds, which is by default 60 seconds. Quite a number, right? And then it does a do while loop, and it awaits an update of metadata from the brokers. You have a microservice sending messages to Kafka. Your sysadmin starts rebalancing your Kafka, or he's doing some crazy stuff with Kafka, or Kafka went down, and your producer tries to await a metadata update because, as they said in the issue, we cannot send a message until we know the metadata. And it's going to block, in this case for up to 60 seconds. Do you want your application, given the information I told you earlier today, do you want to block your application for 60 seconds? I don't. So maybe you're using asynchronous APIs, but it doesn't mean that these APIs are actually asynchronous and non-blocking. So please always verify what you're doing and use the tools, and not just assumptions from the Java doc. And I would like to add more information to talk about how to instrument Reactor, because some of you may want to do similar things, or you just need to do some things that it's not supported in Project Reactor. Let's say you want to know that something is going to be scheduled on some other thread. And reactive programming is all about the message passing, the asynchronous programming, multi-threading, and so on and so forth. So what you can do in the latest Reactor, there's also other methods in 3.2, but this one, I really like this one because it's as simple as schedulers on schedule hook. And now you can intercept every runnable submitted to Project Reactor. And for instance, you want to transfer MDC from one thread to another. And it's a very known issue. If you're using tracing, if you're using MDC from SLF4J, if you're using thread locals, and MDC is efficiently a thread local variable, then you can do it like this. Very easy, less than 10 lines of code. Use it when you need it. There's also Hooks.onEach Operator, not very well known hook, but very powerful one, because it lets you intercept every operator call. It's not the same mechanism as for Reactor debug agent. We were using instrumentation, and here it's part of Reactor internals. We just know when to call this transform. But let's say you want to implement a custom tracing solution, or you want to integrate it with Brave and Zipkin, or Open Tracing, or something else. You can use only each operator, and you'll be implementing an intermediate operator between two different operator calls. So you just intercept them, and you do whatever you want there. You can also implement some advanced logging for debugging when you run your tests, or when you want to debug your advanced reactive code. But on each operator is a bit expensive because you run it on each operator, obviously. So there is another one on last operator, so that when you have your reactive code, and let's say you want to intercept the subscription moment when you call .subscribe, or when some framework like Spring Webhooks subscribes on your publisher, then you can transform it too. And it's also useful for tracing, let's say. So after the information I gave to you, I hope that your Reactor experience will be more like this. So it's fine to work with the fire. Many years ago, we learned how to control the fire, and we started cooking, warming our caves or whatever. So the fire is good, but it's powerful. So we have to know how to control it, and we are good. Takeaways. the most useful slide, most probably, because it contains all the link already gave to you in a short, with a short summary. So please take a look at Reactor tools if you want to improve your production experience. If you ever had to deal with exceptions in productions, and this tool most probably is something you were looking for, and that's the solution. It may or may not eventually become a part of Reactor core. Currently, we are incubating it. So far, so good. So most probably, eventually, we'll add it to Reactor core, and this second dependency would not be necessary. At the moment, you need to add it, but that's just another Reactor project. Take a look at Flux checkpoint and Flux log. Flux log is also a useful operator for logging. You just add Flux log and you see what's going on. Hooks class is still useful even with Reactor debug tool for the hooks, like onEach operator and last operator and others. And you can also read about onOperator debug and use it in tests. Blockhound, the biggest and the greatest tool from this presentation, I think, because it solves a really big pain, and I really hope that, or not, I hope that you never had an issue with blocking calls, but if you ever did, or if you want to make sure that you will never have to deal with the blocking calls, please make sure that you test your code for the blocking calls. And asynchronous APIs, trust them, but verify how they behave. Sometimes the maintainers think that they write non-blocking code, but apparently it's not that non-blocking. And the only good way to check it is to use tools like Blockhound. Thank you for attending. You can always reach to me on Twitter or GitHub or any other mean, and please ask your questions, and I'm looking forward to your stories, how you improved your Reactor experience with the tools I mentioned. Thank you. We should have time for the questions. If you have some, I'm happy to answer. No questions? No questions. Okay. Thanks, everyone, and enjoy the rest of the conference. Thank you.